In mathematical logic, new foundations is an axiomatic set theory, conceived by Willard Van Orman Quine as a simplification of the theory of types of Principia Mathematica. Quine first proposed NF in a 1937 article titled New Foundations for Mathematical Logic, hence the name. Much of this entry discusses NFU, an important variant of NF due to Jensen and exposited in Holmes. In 1940 and 1951, Quine introduced an extension of NF sometimes called mathematical logic, or ML, that included classes as well as sets. New Foundations has a universal set, so it is a non-well-founded set theory. That is to say, it is a logical theory that allows infinite descending chains of membership such as xn, xn1, x3, x2, x1. It avoids Russell's paradox by only allowing stratifiable formulae in the axiom of comprehension. For instance, xy is a stratifiable formula, but xx is not. The type theory TST. The primitive predicates of Russellian unramified typed set theory, a streamlined version of the theory of types, or equality. TST has a linear hierarchy of types. Type 0 consists of individuals otherwise undescribed. For each natural number n, type n plus 1 objects are sets of type n objects. Sets of type n have members of type n1. Objects connected by identity must have the same type. The following two atomic formulas succinctly describe the typing rules and the axioms of TST are: extensionality. Sets of the same type with the same members are equal. An axiom schema of comprehension, namely, if is a formula, then the set exists. In other words, given any formula, the formula is an axiom where represents the set and is not free in. This type theory is much less complicated than the one first set out in the Principia Mathematica, which included types for relations whose arguments were not necessarily all of the same type. In 1914, Norbert Wiener showed how to code the ordered pair as a set of sets, making it possible to eliminate relation types in favor of the linear hierarchy of sets described here. Quinean set theory. Axioms and stratification. The well-formed formulas of new foundations are the same as the well-formed formulas of TST, but with the type annotations erased. The axioms of NF are: extensionality. Two objects with the same elements are the same object. A comprehension schema. All instances of TST comprehension but with type indices dropped. By convention, NF's comprehension schema is stated using the concept of stratified formula and making no direct reference to types. A formula is said to be stratified if there exists a function f from pieces of syntax to the natural numbers, such that for any atomic subformula of we have f equals f plus 1, while for any atomic subformula of we have f equals f. Comprehension then becomes exists for each stratified formula. Even the indirect reference to types implicit in the notion of stratification can be eliminated. Theodor Heilprin showed in 1944 that comprehension is equivalent to a finite conjunction of its instances, so that NF can be finitely axiomatized without any reference to the notion of type. Comprehension may seem to run afoul of problems similar to those in naive set theory, but this is not the case. For example, the existence of the impossible Russell class is not an axiom of NF because cannot be stratified. Ordered pairs relations and functions are defined in TST as sets of ordered pairs in the usual way. The usual definition of the ordered pair, first proposed by Kuratowski in 1921, has a serious drawback for NF and related theories. The resulting ordered pair necessarily has a type 2 higher than the type of its arguments. Hence, for purposes of determining stratification, a function is 3 types higher than the members of its field. If one can define a pair in such a way that its type is the same type as that of its arguments, then a relation or function is merely 1 type higher than the type of the members of its field. Hence NF and related theories usually employ Quine's set-theoretic definition of the ordered pair, which yields a type-level ordered pair. Holmes takes the ordered pair and its left and right projections as primitive. Fortunately, whether the ordered pair is type-level by definition or by assumption usually does not matter. The existence of a type-level ordered pair implies infinity, and NFU plus infinity interprets NFU plus there is a type-level ordered pair. Conversely, NFU plus infinity plus choice proves the existence of a type-level ordered pair. Admissibility of useful large sets NF allow the construction of two kinds of sets that ZFC and its proper extensions disallow because they are too large. The universal set V, because is a stratified formula, the universal set V equals X, X equals X, exists by comprehension. An immediate consequence is that all sets have complements, and the entire set-theoretic universe under NF has a Boolean structure, cardinal and ordinal numbers. In NF, the set of all sets having n elements exists. Hence Frege's definition of the cardinal numbers works in NF and NFU. A cardinal number is an equivalence class of sets under the relation of equinumerosity. The sets A and B are equinumerous if there exists a bijection between them, in which case we write. Likewise, an ordinal number is an equivalence class of well-ordered sets. Finite axiomatizability. New foundations can be finitely axiomatized. Cartesian closure. Unfortunately, the category whose objects are the sets of NF and whose morphisms are the functions between those sets is not Cartesian closed. This is a highly desirable property for any set theory to have. Intuitively, it means that the functions of NF do not curry as one would normally expect functions to. Furthermore, it means that NF is not a topos. The consistency problem and related partial results. The outstanding problem with NF is that it is not known to be relatively consistent to any mainstream mathematical system. NF disproves choice, and so proves infinity. But it is also known that the minor modification of allowing elements yields NFU, a theory that is consistent relative to Peano arithmetic, if infinity and choice are added. The resulting theory has the same consistency strength as type theory with infinity or bounded Zermelo set theory. There are other relatively consistent variants of NF. NFU is, roughly speaking, weaker than NF because in NF, the power set of the universe is the universe itself, while in NFU, the power set of the universe may be strictly smaller than the universe. In fact, this is necessarily the case in NFU plus choice. Specker has shown that NF is equiconsistent with TST plus AMB, where AMB is the axiom scheme of typical ambiguity which asserts for any formula, being the formula obtained by raising every type index in by 1. NF is also equiconsistent with the theory TST augmented with a type-shifting automorphism, an operation which raises type by 1, mapping each type onto the next higher type, and preserves equality and membership relations. The same results hold for various fragments of TST in relation to the corresponding fragments of NF. In the same year that Jensen proved NFU consistent, Grisham proved consistent is the fragment of NF with full extensionality and those instances of comprehension which can be stratified using just 3 types. This theory is a very awkward medium for mathematics, largely because there is no obvious definition for an ordered pair. Despite this awkwardness, is very interesting because every infinite model of TST restricted to 3 types satisfies A and B. Hence for every such model there is a model of with the same theory. This does not hold for 4 types. Is the same theory as NF, and we have no idea how to obtain a model of TST with 4 types in which A and B holds. In 1983, Marcel Krabbe proved consistent a system he called NFI, whose axioms are unrestricted extensionality and those instances of comprehension in which no variable is assigned a type higher than that of the set asserted to exist. This is a predicativity restriction, though NFI is not a predicative theory. It admits enough impredicativity to define the set of natural numbers. Krabbe also discussed a sub-theory of NFI, in which only parameters are allowed to have the type of the set asserted to exist by an instance of comprehension. He called the result Predicative NF. It is, of course, doubtful whether any theory with a self-membered universe is truly predicative. Holmes has shown that NFP has the same consistency strength as the predicative theory of types of Principia Mathematica without the axiom of reducibility. How NF avoids the set theoretic paradoxes. NF steers clear of the three well-known paradoxes of set theory. That NFU, a consistent theory, also avoids the paradoxes increases our confidence in this fact. The Russell paradox, an easy matter, is not a stratified formula, so the existence of is not asserted by any instance of comprehension. Quine presumably constructed NF with this paradox uppermost in mind. Cantor's paradox of the largest cardinal number exploits the application of Cantor's theorem to the universal set. Cantor's theorem says that the power set of any set is larger than from into. Now of course there is an injection from into, if is the universal set. The resolution requires that we observe that makes no sense in the theory of types. The type of is one higher than the type of. The correctly typed version is, where is the set of one element subsets of. The specific instance of this theorem that interests us is, there are fewer one-element sets than sets. The obvious bijection from the universe to the one-element sets is not a set. It is not a set because its definition is unstratified. Note that in all known models of NFU it is the case that choice allows one not only to prove that there are elements but that there are many cardinals between in. We now introduce some useful notions. A set which satisfies the intuitively appealing is said to be Cantorian. A Cantorian set satisfies the usual form of Cantor's theorem. A set which satisfies the further condition that the restriction of the singleton map to A is a set is not only Cantorian set but strongly Cantorian. The Boer-Liefautor paradox of the largest ordinal number goes as follows. We define the ordinals as equivalence classes of well-orderings under similarity. There is an obvious natural well-ordering on the ordinals. Since it is a well-ordering it belongs to an ordinal. It is straightforward to prove that the order type of the natural order on the ordinals less than a given ordinal is itself. But this means that is the order type of the ordinals and so is strictly less than the order type of all the ordinals, but the latter is, by definition, itself. The solution to the paradox in NF starts with the observation that the order type of the natural order on the ordinals less than is of a higher type than. Hence a type-level ordered pair is 2, and the usual Kuratowski ordered pair 4 types higher than the type of its arguments. For any order type, we can define an order type 1 type higher. If, then is the order type of the order. The triviality of the T operation is only a seeming one. It is easy to show that T is a strictly monotone operation on the ordinals. We can now restate the lemma on order types in a stratified manner. The order type of the natural order on the ordinals is or depending on which pair is used. From this we deduce that the order type on the ordinals is, from which we deduce. Hence the T operation is not a function. We cannot have a strictly monotone set map from ordinals to ordinals which sends an ordinal downward. Since T is monotone, we have a descending sequence in the ordinals which cannot be a set. Some have asserted that this result shows that no model of NF is standard, since the ordinals in any model of NF are externally not well ordered. We do not take a position on this, but we note that it is also a theorem of NFU that any set model of NFU has non-well-ordered ordinals. NFU does not conclude that the universe V is a model of NFU, despite V being a set, because the membership relation is not a set relation. For a further development of mathematics in NFU, with a comparison to the development of the same in ZFC, see implementation of mathematics in set theory. The system ML. ML is an extension of NF that includes classes as well as sets. The set theory of the 1941 edition of Quine's mathematical logic married NF to the proper classes of NBG set theory, and included an axiom schema of unrestricted comprehension for proper classes. However, J. Barclay-Rosser proved that the system presented in mathematical logic was subject to the Borel-Forte paradox. This result does not apply to NF. Wang showed how to amend Quine's axioms so as to avoid this problem, and Quine included the resulting axiomatization in the 1951 second and final edition of Mathematical Logic. Wang proved that if NF is consistent then so is ML, and also showed that ML can prove the consistency of NF.